Hi everyone, I'm Sowmiya. I'm a senior machine learning engineer working on perception systems for autonomous vehicles. My work centers on taking models from research ideas all the way through real-world deployment in safety-critical environments. In this talk, I'll share how the autonomous vehicle industry is moving from fragmented perception pipelines to unified end-to-end models and what we have learned while scaling these systems in practice. Before we dive in, here's a quick roadmap. We'll start with the fragmentation problem in traditional perception stacks and discuss why separate models for each task create inefficiencies and hidden failure modes. Then, we'll look at the unified perception paradigm and how a single integrated system can learn shared representations across tasks and sensors. From there, I'll introduce multi-sensor fusion transformers, which are a key architectural enabler for making this approach practical. After that, I'll share some real-world deployment challenges and lessons from production, because scaling perception outside the lab is where most of the complexity really shows up. And finally, we'll touch on foundation models for autonomous driving, which I see as the next frontier for making the systems more scalable and data efficient. By the end, you should have both the technical intuition and the practical perspective behind unified perception. Let's start with the core problem. Most traditional perception systems are highly fragmented. We typically train one model for detection, another for segmentation, and one more for depth, and sometimes even separate models for each sensor. Each of those modules processes the same inputs independently, which leads to duplicated computation, higher latency, and errors that cascade from one stage to the next. But beyond efficiency, the bigger issue is that these models never develop a cohesive understanding of the scene. They're optimized locally rather than globally. So over time, the system becomes complex, brittle, and harder to maintain. The alternative approach is unified perception. Instead of isolated models, we train a single end-to-end system that jointly learns spatial, semantic, and temporal representations. All sensors feed into shared encoders, and lightweight task heads branch out for specific outputs. Because those features are shared, improvements in one task naturally benefit the others. Detection helps, segmentation informs depth, and everything improves together. So we reduce redundancy while actually increasing accuracy. The system becomes both simpler architecturally and stronger performance-wise. One of the biggest enablers of this shift has been transformers. Self-attention lets us model long-range relationships across the scene, which is critical in driving where context really matters. Cross-modal attention allows the network to align camera appearance with LiDAR geometry automatically, instead of relying on AND design fusion rules. And token-based representations make it easier to handle different sensor resolutions and modalities. Together, these properties make transformers a very natural fit for unified end-to-end perception. If we break the architecture down, there are three main components. First, a shared backbone that extracts general purpose features across all sensors. Second, cross-modal alignment networks that project LiDAR and camera information into a unified latent space. And third, temporal fusion modules that aggregate information over time. This temporal component is especially important because a single frame can be ambiguous, but motion across frames reveals intent and continuity. When we train these models, we also train the 2D and 3D elements of it jointly rather than separately. Images gives us rich semantics like texture and appearance, while point clouds provide precise geometry and depth. By combining both these modalities, we get the best of each. This leads to better 3D boxes, more stable depth estimates, and a unified representation that downstream modules like tracking and planning can depend upon. In practice, this joint learning significantly improves robustness. One key lesson from real-world deployment is that sensors don't fail uniformly. Rain or darkness might degrade cameras, while fog or sparse returns can affect LiDARs. So static fusion simply isn't enough. Instead, we use adaptive attention mechanisms that dynamically weight each sensor based on reliability. When one degrades, the system automatically leans more on the others. This gives us graceful degradation instead of sudden failures, which is critical in terms of safety. As soon as we move outside control settings, new challenges appear. Weather changes, geographic differences, and domain shifts all impact performance. And then there are long tail scenarios like construction zones, emergency vehicles, or unusual pedestrian behavior. These rare events matter the most for safety, and they show up the least in training data. So we rely heavily on targeted data collection, balance sampling, and continual learning strategies to cover those edge cases. There's also a big engineering benefit here. Traditional stacks require multiple models, multiple inference passes, and complex interfaces between them. Whereas unified perception simplifies all of that into a single forward pass. That reduces latency, makes debugging easier, and significantly streamlines deployment. From an infrastructure standpoint, this is a huge operational win. Another important trend is supervised, rather self-supervised learning. Labeling autonomous driving data at scale is extremely expensive. So instead, we use techniques like contrastive alignment, temporal consistency, and cross-sensor reconstruction to learn directly from unlabeled data. This lets us scale training to massive datasets without proportional annotation costs and helps capture the long-tail scenarios that are the hardest to label manually. Even with large-scale training data, distribution shift is unavoidable in autonomous driving. Every new city looks different. Lighting changes, road layouts change, and even driving behavior changes. So models that work well in one place can degrade somewhere else. To handle this, we use domain adaptation techniques that allow the system to adjust continuously, including adversarial feature alignment, test time adaptation, and rapid fine-tuning. The key idea is that perception isn't something you train once and freeze. It's something that keeps learning and adapting as the vehicle encounters the real world. Now let's come to the new and hot topic in the industry right now. Those are foundational models. By pre-training on massive driving datasets, we learn strong general-purpose representations that transfer well across tasks. Then we only need lightweight heads for detection, tracking, or prediction. What's especially exciting is zero-shot behavior. These models often generalize to unseen scenarios without explicitly training, which is incredibly valuable when you can't label every possible edge case. So, stepping back, what do we gain overall? We get lower latency because everything runs in a single pass, better accuracy through shared learning, and simpler deployment with fewer moving parts. It's rare to find an approach that improves both performance and engineering complexity at the same time, but unified perception really does both. Ultimately, all of this ties back to safety. Consistent scene understanding reduces error propagation, temporal reasoning improves predictions of dynamic agents, and adaptive fusion maintains robustness when sensors degrade. Together, these improvements translate directly into fewer disengagements and more reliable behavior in the real world. So, unified perception isn't just an architectural choice, it has a measurable safety impact. To summarize, unified architectures streamline perception, multi-sensor fusion is essential, and foundation models combined with self-supervision will continue accelerating progress. As these systems mature, autonomous vehicles become safer, more scalable, and better equipped to handle the complexity of the real-world driving. Thank you for your time. If you'd like to continue the conversation, feel free to scan the QR code and connect with me on LinkedIn.